The U.S. F-15EX Eagle II, the Air Force's latest fighter, is turning heads with claims of unprecedented speed and firepower. Rumors are swirling that this jet could approach hypersonic velocities, challenging the limits of what a conventional fighter can achieve. But how true are these claims, and what would reaching such speeds mean for the U.S. Air Force's edge in modern aerial combat? Join us as we explore the mind-blowing features of the new F-15EX that's turning heads. The F-15EX Eagle II, the newest version of the famous F-15, has stirred a lot of excitement because of its incredible speed. Some people believed it could reach nearly Mach 3, but the truth is slightly different. While it cannot go that fast, the Eagle II can still achieve speeds that are nothing short of amazing, proving its power and advanced design. Many believe the jet could reach Mach 2.9, which is about 2,225 miles per hour at sea level. That number alone would put it close to the record speeds of the legendary SR-71 Blackbird, one of the fastest aircraft ever built. However, this assumption wasn't fully correct. When the actual performance details were made clear, it was revealed that the F-15EX Eagle II's highest confirmed speed is Mach 2.497 in a clean setup. A clean configuration means the jet carries no external weapons, sensors, or pylons, which reduces drag and allows it to fly faster. Even though this number is less than Mach 2.9, it is still an impressive achievement for a fighter jet designed to carry heavy weapons and advanced technology. What makes this even more exciting is that the Eagle II's top speed was not achieved during a special record-breaking attempt. Instead, this performance was observed during normal testing. It shows that the aircraft has the power to push the limits without needing extreme conditions. To understand why this matters, one has to look at the F-15's long history. The original F-15 was built in the 1970s as an air superiority fighter, and it quickly earned a reputation for speed, power, and unmatched performance. Over the decades, it has been upgraded many times to stay ahead of modern threats. The F-15EX is the latest evolution of this design, fitted with the newest avionics, sensors, weapons, and digital systems, while still carrying the raw speed and strength of its ancestors. Being able to fly at nearly 2.5 times the speed of sound is a huge advantage for a fighter jet that's meant to serve as both a frontline combat aircraft and a heavily armed weapons platform. The Eagle II can carry more missiles than any other U.S. Air Force fighter, and combining that firepower with such speed makes it a powerful tool for defense. Even though it does not quite touch Mach 3, the F-15EX proves that speed is not just about records. It's about the ability to perform missions under real-world conditions. With its confirmed top speed of Mach 2.497, the Eagle II stands as one of the fastest and most capable fighters flying today, carrying on the proud tradition of the F-15 family while pushing its legacy into the future. That is not to say that the F-15EX could not potentially push beyond its advertised performance limits. At its core, the fighter is powered by two mighty General Electric F110 GE129 engines. Each of these engines is capable of producing nearly 29,500 pounds of thrust when operating in full afterburner. This immense amount of power gives the aircraft extraordinary acceleration and climbing ability, the kind of strength that makes it one of the most formidable jets in the skies today. Still, for the pilots who will fly the F-15EX in real combat service, it is unlikely that they will ever experience such blistering speeds. While the aircraft might technically be capable of reaching close to Mach 2.5, this can only be done under very specific conditions. To achieve this, the jet must be flown in a stripped-down state, what many refer to as an airshow configuration. This means no pylons, no external stores of any kind, and none of its conformal fuel tanks attached. In this bare state, the fighter becomes a sleek, unburdened machine, able to make the most of its power without the drag of combat equipment. Tests in these carefully controlled circumstances have shown just how much performance the latest F-15 models can deliver. With the engines pushing to their limits, the jet has demonstrated a level of speed and power that leaves onlookers stunned. Yet it is important to understand that these demonstrations are not representative of everyday combat flying. They take place under perfect weather conditions, at optimal altitudes, and within very narrow parameters designed to squeeze every ounce of potential from the aircraft. One of the most puzzling points raised by observers, and even hinted at by the original program manager, revolves around the thermal stresses the aircraft would face at such high speeds. Once an aircraft moves faster than Mach 2, the heat generated by air friction begins to rise dramatically. At Mach 2.5, the thermal loads on the airframe and engines become extreme. The F-15 in its original design was never truly meant to survive long periods at such speeds. It was engineered to peak near Mach 2, not to cruise comfortably at or beyond that threshold. This limitation is not unique to the F-15. Many high-performance jets are restricted not by their thrust or aerodynamics, but by the heat created when air rubs against the skin of the aircraft at supersonic velocities. Even if the engines could push the fighter further, the buildup of heat on surfaces, control systems, and engine components becomes a major concern. Exceeding those limits risks damaging the jet or severely shortening its service life. For this reason, operational pilots rarely attempt to test these upper extremes. In real missions, carrying weapons, fuel, and equipment, the aircraft operates well below its absolute speed record. Instead, its strength lies in a balance of speed, agility, and survivability, all tuned for combat effectiveness rather than record-setting runs. Former Air Force pilots provided insight into the true operational speeds of F-15 jets, emphasizing the distinction between theoretical maximums and practical flight conditions. One pilot, who had flown Strike Eagles powered by Pratt & Whitney F-100PW 220 engines producing roughly 23,500 pounds of thrust each, and later by the more powerful F-100PW 229 engines rated at around 29,000 pounds of thrust, explained that while the airframe and engines could reach speeds beyond Mach 2.5, external components such as paint and antennas would be at risk of damage. He noted that these limits were more about the durability of peripheral elements than the performance of the aircraft itself. Another veteran, Paul Woodford, who flew the F-15C in the 1980s, described the performance he observed during functional check flights out of air bases in the Netherlands and Alaska. He recalled that in completely clean configuration, without pylons or external stores, the C model could reach the speeds of approximately Mach 2.21. Woodford suggested that the newer F15EX, with additional engine thrust, might achieve slightly higher speeds. However, he cautioned that the airframe design and the larger two-seat canopy would impose some aerodynamic limitations, reducing the potential gain from more powerful engines. Woodford also mentioned that the Air Force had made modifications to reduce wear on the jets. He explained that exhaust pedals, often called turkey feathers, were removed from air defense Eagles, and engines were detuned slightly, which had the effect of reducing maximum achievable speed. He predicted that similar limitations would likely apply to the F-15EX, meaning that operational top speeds would be lower than theoretical figures. He estimated that pilots would rarely exceed Mach 2.2, and only for a brief period due to fuel constraints. Another former F-15C pilot confirmed these observations, reporting that he had reached Mach 2.25 at high altitude. He added that while this was impressive, the most remarkable speeds occurred at low altitude, where he recorded 780 knots indicated airspeed at less than 500 feet. This suggested that the aircraft could achieve extremely high speeds under certain conditions, but sustained operation at these speeds was limited by fuel consumption and thermal stress on the airframe. When discussing the potential of the F-15EX to reach its top speeds in regular service, a former pilot explained that while the aircraft had immense thrust, operational limitations would prevent it from fully exploiting its maximum capabilities. He noted that the F-15C, which was comparatively lighter, could reach Mach 2.5 during testing, but only by using the Vmax switch. In real-world operational conditions, jets rarely surpassed Mach 2.3 because of concerns about airframe heating and intake performance. The Vmax switch, located below the left canopy sill, played an interesting role in the legacy F-15's performance. The pilot explained that it could be engaged once the aircraft exceeded Mach 1.1, temporarily boosting engine and afterburner fuel flow by roughly 4%, which also increased thrust by a similar amount. However, this mode had strict limitations. It could only be used for a maximum of 6 minutes and required a full engine inspection afterward to ensure no damage had occurred. The pilot added that although all F-15 jets were equipped with the VMAX switch and it was heavily safety wired, Air Force regulations prohibited its use during normal operations. He had never heard of anyone activating it outside of carefully planned record attempts, suggesting that only the specially modified Streak Eagle might have used it. The Streak Eagle, a stripped-down Fi-15A, had been modified for a series of time-to-climb records in 1975. Its flights focused on achieving the fastest climb rates rather than straight-line speed, but available data indicated that it likely reached a peak of around Mach 2.25. The aircraft was fully cleared of external stores and unnecessary weight, emphasizing the extreme capabilities of the F-15 platform under ideal conditions. These record flights illustrated the aircraft's potential, but also highlighted practical limitations faced by operational pilots, such as fuel capacity, engine safety margins, and airframe stress. Overall, the pilot emphasized that while the F-15EX benefits from more powerful engines and modern systems, its operational speeds would still be constrained by similar factors as previous F-15 models. Even with additional thrust, the airframe's heating limits and intake efficiency created natural ceilings for sustained high-speed flight. In practice, pilots would rarely push the jet to its absolute maximum velocity, reserving extreme maneuvers and top-end speeds for testing, record attempts, or highly controlled demonstrations. He concluded that the combination of immense thrust, advanced aerodynamics, and engine management systems makes the F-15EX one of the fastest operational fighters in the world. Yet operational prudence ensures the aircraft remains safe and reliable during routine missions, preserving both the airframe and engines while allowing pilots to take advantage of its blistering performance whenever required. Even with the most powerful engines, high-speed flight involves careful management to avoid overheating, structural stress, or loss of control, underscoring that performance is as much about engineering as it is about operational judgment. The Streak Eagle's record-breaking achievements were not coincidental, as the aircraft had taken titles previously held by the Soviet MiG-25 Foxbat. Analysts and pilots have long pointed out that the threat posed by the Foxbat was one of the main catalysts for the original F-15's development. The MiG-25, with its extreme speed and high-altitude capabilities, forced Western designers to create a fighter capable of matching or exceeding those performance benchmarks. Its successor, the MiG-31 Foxhound, continues to serve in large numbers within the Russian Air Force. Theoretically, it is capable of reaching speeds of Mach 2.83, with a cruising speed of Mach 2.35. However, during a parliamentary hearing in 2013, the then Russian Air Force Commander-in-Chief, Lieutenant General Viktor Bondaryev, stated that the Foxhound was now restricted to Mach 1.5. This limitation was reportedly due to concerns about the strength and safety of the cockpit canopy transparencies under extreme aerodynamic stress. The former F-15E pilot interviewed for this study noted that the mud-moving Strike Eagle, when equipped with the F100PW220 engines, also featured a VMAX switch. He explained that although the switch existed, it carried numerous warnings about the potential for engine damage, and he never actually used it during operational flights. Nevertheless, the mere presence of the VMAX switch indicated that it was at least theoretically possible for a standard legacy F-15 to approach speeds of around Mach 2.5, provided the aircraft was in a clean configuration with no external stores or pylons. Operational realities, however, meant the switch was rarely, if ever, engaged by active pilots. The stresses imposed on the airframe and engines by high-speed flight, combined with safety concerns and the need to protect pilot careers, effectively limited the use of maximum thrust capabilities. Even in ideal testing conditions, the highest speeds were achieved under tightly controlled circumstances, which were far removed from everyday combat missions. With the introduction of the F-15EX, the aircraft's engines provide significantly increased thrust compared with the original models. This enhancement allows the fighter to maintain impressive high-speed performance while also supporting the expanded weapons loadout and modern systems that were unimaginable for F-15C models from the 1980s. Pilots now have the capability to operate the aircraft in a variety of configurations without sacrificing the power needed for rapid acceleration or sustained supersonic flight. Although practical considerations still prevent regular use of absolute maximum speeds in routine operations. Operational limits of the F-15EX are influenced not just by the aircraft's engines or airframe, but also by the external stores it carries. Analysts noted that every bomb, missile, or sensor pod adds both weight and drag, which in turn restricts the aircraft's top speed. Beyond simple aerodynamics, these stores have their own engineering tolerances, particularly when it comes to kinetic heating during high-speed flight. The friction and heat generated at supersonic velocities can approach levels that some munitions were never designed to handle. Boeing's Rob Novotny, a former Air Force F-15 test pilot and now an executive at the company, emphasized that in practice, the stores themselves represent the real limiting factor for speed. While the aircraft could theoretically reach higher speeds in a completely clean configuration, operational missions with full external loadouts are constrained by the heat and structural thresholds of the stores, rather than the engines or airframe. Representatives from Boeing also highlighted that the F-15EX is more than just a high-speed platform. They explained that one of the main advantages of the aircraft lies in its combination of engine power and weapons-carrying flexibility. With multiple hardpoints and stations for external munitions, the fighter can accommodate a wide array of current and future weapon systems. This capability allows regional commanders and warfighters to select payloads that match specific mission requirements without being limited by internal weapons bays alone. The aircraft's performance, when paired with its loadout versatility, ensures that it can operate effectively in modern combat environments. Boeing indicated that the combination of thrust, maneuverability, and external weapons capacity allows the F-15EX to carry advanced or emerging munitions that may not have existed when earlier versions of the fighter were designed. This adaptability is crucial in contemporary theaters of war, where threats evolve rapidly and mission profiles can vary dramatically. The F-15EX, as a non-stealthy fighter, relies heavily on its ability to carry a wide range of external weapons. Air Force and Boeing officials have generally remained cautious about revealing the exact nature of the new and emerging weapons the aircraft may carry in the future. They have emphasized, however, that the fighter's expanded hardpoints and external stations provide a level of flexibility not available to stealth platforms, which are limited by internal weapons bays. In previous discussions, Lieutenant General David S. Nahom, the Air Force's Deputy Chief of Staff for Plans and Programs, highlighted the F-15EXs to carry oversized weapons that would not fit inside a fifth-generation stealth fighter. There have also been hints that the Air Force intends to use the F-15EX to carry larger air-to-air and air-to-ground weapons, potentially including hypersonic missiles that simply would not fit in the bays or on the pylons of aircraft like the F-5A. This makes the Eagle II uniquely suited to complement stealth fighters by delivering munitions that require more space or greater structural tolerance. Major Kevin Hand, an operational and experimental test pilot with the Air National Guard Air Force Reserve Test Center, has demonstrated the aircraft's ability to operate across a broad flight envelope at high speeds. The Air Force has specifically mentioned an unnamed oversized air-to-air weapon that the F-15EX will be able to carry. Its relationship to the Long-Range Engagement Weapon, or LREW, is unclear, but that program was announced some years ago and has largely vanished from public discussion. The high-speed capabilities of the F-15EX provide a clear advantage for weapons deployment. Missiles such as the AIM-120AMRAAM and the upcoming AIM-260 benefit from being launched from a fast-moving platform, which increases their range and effectiveness. High-speed launches also improve the missile's energy at release, which can extend kill probability and engagement distance. The fighter's speed is particularly relevant for long-range air-to-air missiles, allowing it to fire from a safer standoff position while supporting stealth fighters that provide targeting through data links. The U.S. Air Force plans to acquire a fleet of 104 F-15EX aircraft, including an additional 24 added to the fiscal year 2024 budget. Locations for these aircraft include Portland, Fresno, New Orleans, and Kadena on the Japanese island of Okinawa. Kingsley Field is no longer considered for basing. Training for the new Eagle II fleet will be integrated with the F-15E Strike Eagle Schoolhouse. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.